Hi everyone, it's me again. So for today's final lecture, we are going to discuss about breadth first search. But before we do breadth first search, I wanted us to be able to differentiate the difference between DFS and BFS because we will be able to appreciate the concept of DFS and BFS if we are able to compare both of them together. So let's say we're given this kind of graph. Why don't we make a new one? It doesn't look that nice. How about this one? It looks more confusing. So in DFS, we start with a specific vertex. So let's say we start at vertex 6. Let's pause this so that we can do this one at a time. We start at vertex 6 and then we set it to visited. So 6 has already been visited. We are going to check for all of its adjacent vertices. That's 2, 4, 7, and 5. And we get the smallest one. The smallest one is 2. See, 4, 5, and 7, we don't even touch them yet. We always go to the smallest vertex and we visit that node. So we set that to 2. We visit the node. See, 4, 5, and 6, we will visit them later. We go to the node that is visited. So we're now at 2. We do it again. We look for the adjacent vertices. Adjacent to 2 is only 5, so I'm going to go to 5 and I'm going to check, is 5 already visited? No, it's not, so we go to 5. We check for adjacent vertices again. We have 1, we have 3, and we have 6. The smallest one is 1. So we are going to check 1. Is 1 visited? No, it's not. So I am going to go to 1 and set it to visited. Check for adjacent again. Is there anything adjacent to 1? No, there isn't. So I'm just gonna go back to 5. Next, I'm gonna check for my adjacent vertices again. 3, 6, and 7. The smallest one is 3, so I'm going to check for 3. So is 3 visited? No, it's not. So I'll go to 3. So you will notice the process for DFS is check for my adjacent vertices, visit the smallest one, check for adjacent vertices, visit the smallest one that isn't visited yet, check for adjacent vertices, visit the smallest one that hasn't been visited yet, and so on until you actually visit all of the different elements. BFS is different. In BFS, rather than ignoring other adjacent vertices and visit the first smallest adjacent vertex that's not yet visited, BFS will visit all of its adjacent vertices first. And it makes use of a different data structure to keep note of how we will visit our nodes. And it makes use of a queue data structure. So we have this example here, and I will show you the process rather than having to go through like a specific PowerPoint. This looks better. So let's start with any vertex, and let's just say I'll start with vertex 6 lang gihapon. So let's pause. So you will notice when I started, I put 6 into my queue, meaning I'm starting at 6. I'm going to check for all of my adjacent vertices in 6. I have 2 and I have 5. I'm going to visit 2. When I visit 2, I'm not actually going to 2, I'm just adding it into the queue. Do I still have any other adjacent vertex? Yes, I do. I have 5. So I am going to set, and take note, I did 2 things. I set 2 to visited, and I added 2 to the queue. So I'm going back to 6. Do I still have adjacent vertices? Yes, I do, which is 5. So I'm going to check, is 5 already visited? No, it's not. So what do? I set 5 to visited, and I inserted 5 into my queue, or I did an NQ, which is, if you can recall, it's an operation on queue wherein we insert an element to the last. Insert last. So I'm still at 6. Do I still have any elements or adjacent vertices in 6? Wala na. So I will DQ 6. 6 was removed from my queue, and now I'm going to check for 2. I'm going to check for the adjacent elements in 2, or adjacent vertices. 2 and 0. I actually have many adjacent vertices. I have 0, I have 5, and I have 4, but we always check for the smallest one. Depending on the problem, if they want to check in descending order, pwede pod. I'll use the biggest one. So it depends on the instruction. So in this case, I'm checking for ascending, so I'll start with the smallest one, which is 0. 2 points to 0, or 2 has an arc to 0. Is 0 already visited? No, it's not. So if it's not visited, what do? We set 0 to be visited and we add 0 to the queue. 0 is visited, so add 0 to the queue. We check for the next adjacent vertex. We have 4 and we have 5. 4 is smaller, so I'm going to 4. Is 4 already visited? No, it's not. So I'm going to set that to true and insert it into the queue. I'm going to check again. 5. Is 5 already visited? Yes, it is. So what happens when it's already visited? I don't do anything. So I didn't do anything. So after that, do I still have any other adjacent vertex? No, I don't. So I DQ. And I go to the next, which is 5. 5. I'm going to check for the adjacent vertices of 5. I have 1, I have 6, and I have 7. I'll start with 1. Is 1 already visited? No, it's not. So what do? I set it to visited and I insert 1 into the queue, or I NQ 1. I'm going to do it again. 6 and 7. 6 is smaller, so I'm going to check for 6. Is 6 already visited? Yes. No, it's not. So I am going to set this to true, insert into the queue. So look at that. Hello? Wrong. Sorry guys, I made a mistake. I don't know why in this visualization 6 wasn't set to true. But we should have set 6 to true at the start because 6 was our starting vertex. I forgot. So this should have been true. So that's why you'll notice I was shocked. It didn't do anything with 6. This should have been set as true. True na gini siya daan sa sugod pa lang. Because if I skip back to the start, I don't want to skip back to the start. But you get my point. I started at 6, so this should have been true. So when I checked 6, has 6 been visited? Yes, it was. So I'm going to go to the next vertex. 7. Is 7 visited? No, it's not. So I'm going to set this to true, insert it into my queue. Does 5 still have adjacent vertices? Wala na. So I'm going to DQ. I'm now at 0. 0 is adjacent to 2 and 3, so I'll start with 2. 2 is already visited, so I don't need to check 2. I'm going to check 3. Is 3 already visited? No, it's not. So I'm going to set it to true, insert into the queue. And then I'm going to 3. I'm not going to 3, sorry. I am going to check for adjacent vertices. Is there still adjacent vertices? Wala na. So I'm going to DQ. And go to the next in my queue, which is 4. I'm at 4. What are the adjacent vertices of 4? We have 7. Is 7 already visited? Yes, it is. So I do nothing. Is there still any adjacent vertex? There are none. So DQ 4. And I go to 1. 1. I have only one adjacent vertex, which is 3. Is 3 already visited? Yes, it is. So I don't do anything and then I DQ. I'm now at 7 because my queue says I should be at 7. 7 is adjacent to 6 and it doesn't actually point to anything else, so I'm going to check 6. Is 6 already visited? Technically it was at the start. I don't know why it's not visited in this visualization tool, but it's supposed to be visited already. So 7, is 6 visited? Yes, it is. So do nothing. Are there still any adjacent elements or adjacent vertices to 7? Wala na. So I'm going to go to the next. 3. The last one in my queue is 3. 3 is adjacent to 7, so I check 7. Is 7 already visited? Yes, it is. So I do nothing. Look for other adjacent vertices. There are none, so I DQ. So once my queue has been depleted, mahurot na gani akong queue, BFS is over. If there are still elements that are not yet visited, you call BFS again. The result will just be similar to what we had with, not with Dijkstra's, but with our graphs. So in theory, you could call BFS here as well. So for example, let's do BFS 4. I do 4, I visit 5, and I visit 6. In my queue, it would be 4, 5, 6. Are there still any adjacent elements to 4? Wala na. So I DQ 4 and I go to 5. 5 adjacent to 1. 1 is not visited, so I do 5, 6, insert 1 into my queue. And 5 doesn't have anything adjacent, so I DQ 5 and I go to 6. So 6. And I think you get the point. So you could also try to do BFS on this graph and show me what you did. Okay? Good. So I think that's it for BFS simulation or the process with BFS. I hope you guys got it and let me know if you have any questions. Bye.